All right, welcome back. So we have a little bit more of section 6.1 to do, and then we'll finally be ready to start section 6.2. So let's get started. So I wanted to begin by doing a little bit of review on how we can find the area under the standard normal curve by using the table. So for this first one, we have a z of 0.44, and we want to find the area to its left. So our standard normal table tells us the area from negative infinity up to a particular z. So we have 0.44. So the whole number is 0. The tenths place is 4. The hundredths place is also 4. So for 0.44, it will be 0.67. So 0.67. Okay, so working our way across next. Here we have a z of negative 1.04. So if this is negative 1.04, then there's a couple of steps to this. For one, we want the area to the right of that. So thinking about it using symmetry, this would be the same as the area to the left of positive 1.04. So if this were positive 1.04, the area to the left would be the same as the area to the right of negative 1.04. So let's look up 1.04 in the table. So 1.0 and then the hundredths place 4, 0.8508. Okay, make sure that you understand that before we go on. All right, so next, this one we'll have to do, this one and 12 we'll have to do in two parts. We want negative 0.84 and then positive 1.28. So we're going to actually need the difference between these two areas. So first of all, the probability that z will be less than 1.28. So getting that out of the table. 1.2 is here, and then the hundredths place 8. 0.8997. Okay, 0.8997. All right, so that would be the area from negative infinity up to that line. We need to find a way to take off that little white part that is on the left of negative 0.84. So how to do that? So again, once again, using symmetry, if we had positive 0.84, the piece that we need to cut off is to the right of that. So we will look to the left of 0.84. 0.8 is here, hundredths place is 4, 0.7995. Okay, this is 0.7995. The area under the whole curve is 1, so 1 minus 0.7995 is going to equal 0.2005. That's the area in the right tail here. And so that would be the area in the left tail up at the top shown in purple. So we'll take the 0.8997 that we calculated a few minutes ago and subtract from it 0.2005. Okay, get 0.6992. All right, so that's probably the most complicated kind. Number 12 is going to play out similarly. So take a minute and try that, and I will put the answer here into the notes. So the area for number 12 works out to be 0.6063. So make sure you're able to figure out how to get that using the same method as we had done in number 11. If you can't figure it out, let me know and we can work through it together. Okay. All right, so in the next two examples, we're working backwards. What we were doing in the last examples was given a z-score, we wanted to find the area. Here, we're given an area and we want to, or probability, and we want to recover the z-score. So for the number 13, we have an area to the left of z of 0.8907. So looking in the body of the table for something close to 0.8907, that's actually right exactly in here, 1.23. Given an area of 0.8907, the corresponding z is 1.23. Next up, we have 0.305 to the left. 0.305 is less than 1/2. So that will be a negative z value. So you'll notice on our z table, the smallest values we have for probabilities are 0.5. The reason for that is because the area under the whole curve is 1. And so if we're starting at or beyond 0, for all of our z's, we will have probabilities bigger than 0.5. So for negative z's, it's negative because it's to the left of 0, we'll need to subtract from 1, get 0.695 for that. So then the probability, let's redraw this so that there's a positive z. So we have a probability of 0.695 associated with a positive z. So 0.695 looks like right there, 0.51. That's positive 0.51. So then for the actual question in number 14, it will be negative 0.51. Okay, two more. For this next one, we want to find the z-score that separates an area of 0.079 to the right. So then again, subtracting from 1, because our table just tells us the area on the left of z, we'll get 0.921. Again, how we got that was 1 minus the 0.079 that is on the right. Looking in the body of the table for 0.921, or what's closest, 9207, 9221. So it looks like 9207 is going to be the closest, 1.41 for our z. All right, so last one of these. For this one, we want to know which two z values would separate off an area of 0.03 in each tail. So again, our table tells us the area from negative infinity up to a positive z. So let's try to redraw that just a little bit. If we're going to have 0.03 in the right tail, then that means that all the rest of the area is 0.97. So looking in the body of the table for 0.97, the closest we can come is 0.9699, and that will be 1.88. So 1.88 will give us a area of 0.9699. So our Z is 1.88. Using symmetry, then, the two Z values are 1.88 and negative 1.88. Take some practice to get used to using the Z table. Make sure you spend a little time with it because soon enough we'll be adding to this story problems at the beginning, and this part will be just the second half of the problem. So it's good to get a lot of practice at working with the table. All right, let's try one more. So we want to find the values of Z that separate the middle 99% from the extreme 1%. So a sketch, as always, is going to help. So we want the middle 99% separated from the extreme 1%. Using symmetry, if we have 1% split among the two tails, very symmetric. If we have 1% split among the two tails, a little better, then half of 1%, which is 0.01 as a decimal, will be 0.005. So we'll have 0.005 in the right tail and 0.005 in the left tail. So then once again, we know that our table tells us the area up to a positive Z. So subtracting that right tail's 0.005 from 1, we should have 0.995 to the left of the Z that we're looking for. So once again, looking in our table for 0.995. .9949 and 9951. So these two look like they're pretty close. They're actually equally close, so we could just take the higher of the two. That will be 2.58. Okay. That will be our final answer. Okay, we had seen this notation last time. One more practice with it. The notation Z sub alpha denotes the Z-score that has an area of alpha to its right. So if we want to find Z 0.01, then that means we want to know what Z-score would cut off an area of 0.01 on its right. Well, if 0.01 is on the right, then 0.99 will be on the left. Again, looking in the body of the table for 0.99. Looks like this is as good as it gets. 2.33. Our Z is 2.33. Now we want a Z of 0.025. So we want to know a Z value that gives an area of alpha to its right. Here alpha is 0.025, so we want 0.025 to the right. Again, if we want 0.025 to the right, then that means we need 0.975 to the left, because the area under the whole curve has to add up to 1. Looking in the body of the table for 0.975, it will be 1.96. 1.96 for our Z value. Z 0.025 is 1.96. Most often, we'll be using the table to help us figure out these probabilities. We saw before how to use technology to get probability values given a z. The inverse procedure, that is, given a probability, find the z value, we can also use technology to do that. So on Excel, the function is norm_inv, so the inverse normal distribution. If we want to find z so that the area of 0.95 is to the left, which is z.05, we'll put 0.95 as the first input, and then again you have to put in the mean and standard deviation. If you're using a TI-83, it's under the distributions menu, and we're going to use the inverse normal function. If anyone's using R, the function for this is qnorm. And by default, it uses a mean of 0 and a standard deviation of 1. For our purposes, we'll be able to just use the table. All right, so I have a couple of more examples of finding areas. And so I'm going to just put the solutions here in the notes. If you have any questions on them, let me know. All right, so this is how these last three examples play out. For greater than 0.82, we'll again use basically the complements rule. So we need the area to the right, so we'll find the area on the left using the table and then subtract from 1, giving 0.2061. For number 20, we just wanted the area less than 1.96, so that was a straight table lookup, 0.975. For 28, it took more work, negative 1.93 to negative 0.45. Using symmetry, if we flip that whole picture across the 0 line, it'll be the same area as you'd get between 0.45 and 1.93, both positive. Looking at both of those values in the table, the probability that corresponding to a z less than 0.45 is 0.7088. For less than 1.93, it's 0.9732. Taking the difference of those two, it's 0.2644. All right, so we're finally ready to start section 6.2. And so basically what this is about is the table that we've been working with is suited for a distribution that has a mean of 0 and a standard deviation of 1. Of course, in a lot of real applications, that's not the case. You don't always have a mean of 0 and a standard deviation of 1. But also, you can't have infinitely many different tables to work with. So what we'll do is we end up making a little transformation from whatever normal distribution we're given in the first place, that is a non-standard normal distribution, to a standard normal distribution. And we'll do that using this z-score formula. Z is the difference between x and mu, so how far is x above or below the mean, divided by the standard deviation. So this transforms from a non-standard normal distribution to standard normal distribution. So we'll use this z-score formula to turn the numbers in whatever problem we're working on into basically the standard normal distribution, and then we'll look up values for the table. So let's try it on this example. So here it says a company manufactures engine parts. The diameters of the parts are normally distributed with a mean of 3 inches and a standard deviation of 0.02 inches. If we select a part at random, we want to know the probability that that engine part is below 2.995 inches. So it's going to be important to make a little picture. So the distribution we are given has a mean of 3. We're interested in being below 2.995. Of course, our table has a mean of 0 and a standard deviation of 1. And so we need to figure out what is that z-score first, because I can't look up 2.995 in my table. I need to find the correct z-score for that first. Z is x minus mu over sigma. We'll have 3 minus 2.995. Sorry, other way around. X is 2.995 minus mu divided by our sigma, which was 0.02. So let's see what that is. That's negative 0.25. Okay, so now we can look that up in the table. So we have now basically a z of negative 0.25 So I'm going to use symmetry and a positive 0.25, and we'll need to figure out that right tail area. So for 0.25, it is going to be 0.5987 on the left. So that will be to the right of negative 0.25. So then 1 minus 0.5987, 0.4013. So the final answer, the probability is 0.4013. Okay, so the overall here is we're given a distribution that had a not zero mean and a not one standard deviation. So we first used this z-score formula to help translate it into a normal distribution. We found our z value, and then we had to do a little playing around to find the probability. Okay, second part, and then we'll be done with this. We're to determine an interval in which about 95% of part diameters will fall. So let's again start with a little picture. So we need to figure out where will 95% of those most typical part diameters fall. So again, using symmetry, if 95% of the data is in the middle, that means that 5% is in the two tails, or 2.5% in each tail separately. So then, if we have the negative infinity up to our z, that will be 0.95 plus 0.025, or 0.975. And so that will be, if we have a probability of 0.975, that will be a z of 1.96. Using symmetry, we'll have 1.96 and negative 1.96. Of course, these are not diameters for the parts, right? These are standard normal values. So we need to turn these into inches, right? Inches. So let's do that. So we're given z values, and we need to turn them back into x's. So for 1.96, which is a z, 1.96, that z, is x minus mu over sigma, and that's x minus, our mean was 3, our standard deviation 0.02. Okay, so here's your algebra prerequisite coming into play. We have 1.96 is x minus 3 over 0.02. So we need to solve that for x. So multiply both sides by 0.02. And then we'll add the 3. So x will be 3 plus 1.96 times 0.02. And that's 3.0392. Okay, so now we're going to try the same thing for negative 1.96 for the shorter engine parts. So we'll have negative 1.96 will be x minus mu over sigma. And so then again, we'll solve that for x. X will be 3. I'll do it in a couple steps, sorry. We'll have negative 1.96 times 0.02 equals x minus 3, and then we'll add 3 to both sides. So 3 minus 1.96 times 0.02 will be our x. So x is going to be 2.9608. Okay, so what does this means? That if we were to go out and collect a big batch of these engine parts, that we would expect 95% of them to be between 2.9608 inches and 3.0392 inches. All right, so the procedure we followed for this part was we started with an area, basically, the probability or percentage of the data lying in a certain range. We worked backwards to help us find the corresponding z values, which were plus and minus 1.96. Then for each of those, which is a z value, we needed to turn them back into x's. So for 1.96, we went through a little algebra to get 3.0392. And then for negative 1.96, we again went through a little bit of algebra to get 2.9608. So I'll leave it to you to do a little bit of math there and determine that the differences from the mean, which was 3, the differences from the mean are equal on both sides. All right, so that's it for now. We will continue with section 3.2 next time.